sharing. Yeah.
Okay.
Let me do it like this then maybe.
Yeah, of course.
Okay. So yeah, thank you, Marty, and thank you all the organizers for organizing this and giving us the opportunity to present our work here. So I will be talking about universality in finite time quantum engines. So it is done in collaboration with Revati and Uma in IIT Palakkad in southern India and with Adolfo del Campo in Donostia International Physics Center in Spain. So as the name suggests, I'll be mainly talking about universality in finite time quantum engines. So the main question is, let me give the context. In infinite time quantum engines, the power goes to 0 because power is inversely proportional to the total time period of the cycle. And efficiency, at least for quantum engines powered by thermal buds, the efficiency is less than the Carnot limit. But in finite time quantum engines, it operates at finite power because, of course, the cycle time is finite. However, the efficiency is reduced because of these non-adiabatic excitations. And these non-adiabatic excitations, usually they depend on the microscopic details of the working medium of the setup, how we do the unitary, non-unitary strokes. So the question that we ask is, if there is any universality in these finite time quantum engines. So now where to look for universal behaviors? So by universality, I mean that different working mediums, different setup will behave similarly. So phase transition is a nice place to look for universality because they are usually associated with universal behaviors. So for example, this paper in 2016 by Campisi and Fazio, they showed that thermal fluctuations in a critical quantum engine can be very beneficial. However, here we'll be looking at quantum fluctuations and from a different perspective. So first, then I'll show how to design a many-body quantum engine operated close to phase transitions and then check if such an engine can show universal behavior. So just the overview is first, I will give a brief introduction to quantum phase transitions. Maybe many of you are already familiar with this subject, but still just to remind you. And then I will talk about how to design a many-body quantum critical engine. And finally, if I have time there, I will just give some specific example with a free fermionic working medium, a transport sizing model, and finally I will conclude. Okay, so let's start. This quantum phase transitions at temperature 0 that happen due to quantum fluctuations. So classical phase transitions, like say water to steam or water to ice, they are because of thermal fluctuations. However, in quantum phase transitions, the transition occurs due to change in some Hamiltonian parameter. One quite well-studied example is paramagnet to ferromagnet. There can be also, say, Mott insulator to superfluid transition. And a crucial thing of this quantum phase transitions is the energy gap between the ground and the first excited state vanishes. And this is crucial because from the time energy uncertainty relation, the time scale, which is inversely proportional to the energy gap, it diverges. And also the length scales diverge. And what it means is, because of this divergence, microscopic details of the system become irrelevant. That is, only the long length scale properties, like say the symmetry, dimension, range of interaction, they become the only important characteristics. And there are universal scalings in terms of critical exponents, which again depend only on these long length scale properties of the systems. And these critical exponents are, for different systems with that belong to the same universality class, can have same critical exponents. So using this, first let us look at how these universal scalings work. Yes. So like there is a Kibble-Zurek scaling. Basically, you can think of this slide as describing the non-adiabatic dynamics in one unitary stroke of an Otto cycle. Like in a unitary stroke, there are excitations, and what this Kibble-Zurek mechanism and the adiabatic impulse approximation, what it says is a system evolves adiabatically away from a critical point, while non-adiabatic excitations result close to criticality. So this energy gap delta it goes to 0 close to the critical point lambda is equal to lambda c, where lambda is some parameter of the Hamiltonian which is changed. So away from the critical point, the time scale that is 1 by delta, because of the time energy uncertainty relation, away from the critical point, this time scale is very small. And close to the critical point, this time scale 1 by delta diverges because delta goes to 0. However, there is always competition between this inherent time scale of the system and the time scale that is associated with the change of Hamiltonian that is given by delta dot. Again, delta is the energy gap. So away from the criticality, this 1 by delta is always very small, and so this time scale wins. But close to criticality, we get, the system does not have enough time to evolve, follow the ground state, and we get excitations. And following this kind of reasoning, one can have the Kibble-Zurek scaling, which says, for example, if the parameter Hamiltonian parameter is quenched linearly at a finite rate 1 by tau, you can think of this tau as say the duration of an unitary stroke. The defect density, that is the density of excitations, goes as tau to the power of the scaling exponent minus nu d by nu z plus 1, where d is the dimension of the system and nu z are critical exponents, which again different systems of the same universality class usually share same critical exponents. So just to a little bit more about the critical exponents. So from this Kibble-Zurek scaling, what we can see is in many cases, or this excitation energy, like in a unitary stroke, if it is a finite time autocycle, when the unitary strokes are of finite duration, the system gets excited. And in such a case, like in a, the excitation energy is given by this tau to the power of minus nu d by nu z plus 1 for quench across the critical point. However, if the quench finishes at the critical point, the scaling is changes to this, that is tau to the power of minus nu d plus z by nu z plus 1. Here d is the dimension of the system, nu is the correlation length exponent, which just says how the correlation length diverges as a function of the distance from the critical point. Here nu is the exponent, and z is the correlation time exponent, dynamical exponent, which says how does the time diverge as a function of the correlation length. And the universality arises because in general these critical exponents do not depend on the microscopic details of the system. So now we'll use this theory to see if we can say something about universality in finite time autocycles, finite time auto engines. However, it is not simple because this Kibble-Zurek mechanism and dissipation don't always go together. What I mean is thermal fluctuations that occur at any non-zero temperature, it can be expected to destroy signatures of quantum phase transitions because thermal fluctuations dominate quantum fluctuations at non-zero temperatures. And a quantum engine, whether it is a Carnot or a Otto or any engine, usually involves multiple unitary and non-unitary strokes and thermal fluctuations, which would in general, may invalidate the Kibble-Zurek mechanism or just, destroy all signatures of this quantum phase transition. So it is a non-trivial question. However, let us look at it a little bit more rigorously. So let me just, quickly describe the autocycle, which is like a traditional autocycle. Say we take a many-body system, which can be a spin chain or even a high dimensional system. So these are the 4 strokes. So the first stroke, the Hamiltonian is kept constant with lambda is equal to lambda 1, and it is coupled to an energizing bath. The bath can be thermal, non-thermal, does not matter, but some energy enters like Q in, and it goes to B. Then the lambda 1 is changed to lambda 2. There is this, it crosses the critical point in this unitary stroke. Then it is coupled to the cold bath or a decaying bath in which the energy is dumped into the bath. And finally, in the 4th stroke, we again go across a unitary stroke, that is across a phase transition. So Kibble-Zurek mechanism, if it is present, it will be present in either this stroke or this stroke. However, as I said, because this autocycle involves also this dissipation and thermal fluctuations in these non-unitary strokes, I mean, there is no guarantee that this scaling would hold. Usually these thermal fluctuations here and here will destroy these universal scalings. So what to do? However, what we find is that if we are careful in designing the machine, then under some quite general conditions, we can design the machine in such a way that we can still get universality in the output, like the power, efficiency at maximum power. How to do it is, we take this Otto cycle in which we take the decaying bath or the cold bath at a very low temperature. It does not have to be exactly absolute zero, but it has to be, temperature has to be much less than the energy scale of the system, so that the working medium goes close to the ground state. Then we do this unitary stroke, in which, of course, at the end, the Kibble-Zurek mechanism is followed in this stroke because it is at 0 Kelvin. And the excitation energy for going across the critical point is given by this Kibble-Zurek scaling law. And then in this stroke, we need a bath which takes us to a unique steady state. That is, the final state cannot depend on the initial state. And then what we do is we do this quench, and the one condition that we need is the temperature. If it is a thermal bath, the temperature of the energizing or hot bath should be very high, or the quench is very fast. From B to C, the unitary quench is very fast, so that the system does not get time to evolve from B to C. That is, the state remains the same. And finally, again, we couple it to the cold bath and come back to the initial, the D point. In such a case, what happens is one can see that the energies or these three strokes give time the tau independent values, that is the energy, the work or the heat input and heat output. So in such a case, what one can show is that the input energy is given by the input energy in the infinite time Otto cycle limit minus the excitation energy, which can be found from the Kibble-Zurek law. And the output energy is same as that we would get in an infinite time Otto cycle. So using all this, combining all this, what we find is that the output work follows universal scaling. That is, the work output minus the output work in the infinite Otto cycle limit, this difference scales as this tau to the power of minus nu t plus z by nu z plus 1, if the stroke is still the quantum critical point. That is, if it finishes here and we couple the hot bath here at the red line. However, if we go across, the scaling changes. However, the universality still holds, the universal scaling in terms of critical exponents. And so what we see is that the universal scalings in finite time Otto engines can be expected under very general condition. Them being the cold bath should be at very low temperature. That is, the temperature is much less than the energy scale of the system. The unitary stroke from D to A is at a finite rate tau, which basically gives the scalings. The energizing bath takes it to a unique steady state that does not depend on the initial state. And the hot bath is very high temperature, or the unitary stroke B to C is very fast. So using this, these are quite general conditions, and using this, we just see that all the performance of this engine follows this universal scaling laws, like the power output or the optimal quench rate for maximum power. That is the, the duration of the unitary stroke. We can think of it as like this, or the efficiency at maximum power, all follow universal scalings in terms of this quench rate, or in terms of the duration of the unitary stroke tau. So here R is some system dependent constant, and this X is 1 or 2 depending on whether we reach the critical point or go across the critical point. But nevertheless, these critical exponents, they introduce the universality.
Sorry, Victor, you have 5 minutes left,
okay.
including questions.
Okay. So what we found is that Kibble-Zurek mechanism, it connects this quantum phase transitions with quantum thermodynamics, and we can use these results to say it may help in optimization of quantum engines, in the sense that once we know these laws, we can use this best possible material to design quantum engines. Just as an example, say we want to maximize the work even in presence of non-adiabatic excitations, then what we can do is we know that this work in the finite time minus the infinite time is given by this scaling. So if we take a system with high dimension, that is high d, then this thing becomes very small, and then the work output is almost equal to the work output of an infinite time Otto cycle. And we also check this using some specific examples. Say we have a fermionic working medium in which there are fermions which can hop between different sites and couple to local berths. And I'm not going into the technical details, but we can go to the Fourier space and then write the master equation where ck dagger are annihilation creation operators and solve it. There also we see that for locally thermal berths, the efficiency is also bounded by some eta max, which is given by universal exponent z, and eta max increases with increasing size. However, it is not a tight bound. So, I mean, large system size can be beneficial for high increasing efficiency. And we also check this with a transversalizing model, which has a critical point from ferro to paramagnet. And we checked that this numerically also we found this the output power, output work, or power, they all match the critical the scaling laws, whether we cross the critical point or reach the critical point. So yeah, I am towards the end. So to conclude, what we saw is that there is universality in work, power, efficiency at maximum power in quantum auto engines operated close to quantum phase transitions. And one can use this universality to design optimally performing quantum engines by choosing the best possible material or with best possible, say, critical exponents or dimension. And next steps might be to enhance the performance of quantum critical engines through shortcuts to adiabaticity, because close to criticality, the non-adiabatic excitations are enhanced. And also look for universality in other kind of quantum engines like Carnot engines or two-stroke or something like that. So thank you.
Thank you very much for the very interesting talk. Are there questions? I don't see them in the chat, but okay, maybe I'm missing. Okay, otherwise, I quickly start. In the numerics that you showed, so these are exact results?
Exactly, yeah. I mean, this transversalizing can be exactly solvable by doing Jordan-Wigner transformation and going to momentum space.
So it's finite size.
It is finite size, yes.
Yes. But you already see the scalings.
Yes, I mean, finite still means like above 100 sites or something, because it can be broken down into independent two-level systems.
Okay. Otherwise, I don't see questions. So since we are not very good on time, we'll move to the next talk. Thank you very much again.
Sorry, I think there was a hand raised.
Okay, sorry, I'm not good at the...
Okay, let me allow
to
Tiago
ask the question. Now, yes, Tiago, so I will...
Sir, Tiago, you can talk. You can ask a question.
Thanks.
So, I mean, so as you're thinking about phase transition, I guess you're working with a macroscopic system somehow. And I was also wondering that the Kibble-Zurek mechanism can also happen at classical phase transitions, no?
Yes.
So could you imagine that if you have a classical gas, macroscopic one running engine, a classical engine, and you have a phase transition, you could also have something similar to what we are showing?
I expect, for example, in this paper, Campisi and Fazio, as far as I remember, they checked across the classical phase transition. So there also they used, they did not really use Kibble-Zurek mechanism, but they used some critical exponents and to show that this efficient power can be non-zero at Carnot efficiency. Or anyways, so there also they used this critical exponent. So I would guess something similar we can see also in classical phase transitions.
Okay, thank you.
Okay, thank you again for the next talk. I think now there are no more questions. So we move to